from the given system, so here we have a classical system. And in this classical system, there will be coordinates required to describe the motion of this particles in this classical system. So according to that, we have the system, that is the Lagrangian, given in terms of the position, the velocity q dot, and time. So Lagrangian is a function of q dot and t, where t is the time. Now Lagrangian is equal to T minus V, where T is the kinetic energy, and V is the potential energy. So differences in kinetic and potential energy gives you the Lagrangian, and through this our aim is to calculate the Lagrangian, that means to find out the kinetic energy and the potential energy of the system. For that we need the coordinates, generalized coordinates, and we need to find out x, that is if you are considering the Cartesian coordinate system, you will have x, y, and z. Corresponding to x, y, z, we have x dot, y dot, and z dot as the velocity. And once you got this, we can find kinetic energy as half m x dot square plus y dot square plus z dot square, and we have the kinetic energy, that is this is equal to T, and the potential energy will be equal to V of x, y, and z. This can be gravitation, electrostatic potential, it can be anything. So now let us look into different classical systems. Before going to the construction of Lagrangian, there are few coordinate systems or rules that we need to follow. Now this is a coordinate system. This is the first quadrant, second, third, and the fourth. Now this plays an important role in finding the values of x and y. So how to give the sign to different points. For example, if you have the position of the particle at the first quadrant, you have x comma y both are positive, and in the second quadrant x is negative, y is positive, and on the third quadrant both x and y are negative, and in the fourth quadrant x is positive and y is negative. Okay, so this is the general criteria of giving the positions. Usually for finding the kinetic energy, it hardly matters, because we are considering the squares of the position or the velocity squared, so it actually becomes the positive value. But when you're considering the potential energy, where for example mgy, so you need to know the value of y exactly. So actually this differs, the values of x and y differs as the origin changes. In this system, we have x, y and z as the coordinates, and there is a particle with the mass m moving in this space randomly. Okay, so it's a random motion. So the kinetic energy of this particle T is equal to half m x dot square plus y dot square plus z dot square. So this is the kinetic energy. And the potential energy, so this particle, if it is in under the gravity, that means gravity will be always acting down, so it will be mg, and this is the what is going downwards is the x axis, so it will be mgx. So potential energy will be mgx. And in case if there is any other potential acting on mass m, that also can be included, which can be function of x also, y, z, etc. So the Lagrangian L is equal to t minus v, so that's equal to half m x dot square, this is within bracket, plus y dot square plus z dot square minus potentially mg x. Here we have a two-dimensional surface and the particle is moving in xy, or you can also write it in terms of r and theta. So for 2D surface, or these plane polar coordinates is generally used for central force problems. Central force. Central force problems, and according to the figure, we have x is equal to, so this will be, sorry, this we will consider as y, and this is x. So here we have x, sorry, this is y, and this is x. So x is equal to, if this is r, this will be r cos theta, and y is equal to r sin theta. Now our aim is to find out the first derivative with respect to time, that is x dot is equal to r dot cos theta plus r sin theta times theta dot. Here we will have a minus sign for derivative of cos theta. So now y dot is equal to r dot sin theta plus r sin theta derivative is cos theta, theta dot. Now we need to find out x dot square, which is equal to r dot square cos square theta plus r square sin square theta, theta dot square minus 2, sorry, yeah, so minus 2 r cos theta, r sin theta cos theta, r sin theta cos theta, r dot theta dot, r dot theta dot, and y dot square is equal to r dot square sin square theta plus r square cos square theta theta dot squared plus, so we have plus 2r sin theta cos theta r dot theta dot. Now we need half m x dot square plus y dot square, so that will be equal to these two terms will get cancelled, so this is r dot square cos square theta plus r dot square sin square theta is nothing but r dot square, and here you have r square theta dot square, so this is r dot square plus r square theta dot squared. So cos square theta plus sin square theta gives you 1, and this is the kinetic energy T, so multiplied by half m, where m is the mass of this particle. Now if you need V potential, if you assume this particle is in gravity, we have mg y, and what is y? Y is equal to r sin theta, so mg r sin theta. So Lagrangian will be equal to half m r dot square plus r square theta dot square minus mg r sin theta. So looking into simple pendulum, here we are considering this as the origin, that is 0 0, and you see this is in the fourth quadrant, this is the y, and the position x is here, so this is angle theta. The length of the simple pendulum is L, so x is equal to, from this point to this is L sin theta, and y is equal to L cos theta, but with a minus sign. Why? Because it is in the third quadrant, sorry, the fourth quadrant, where x is positive and y is negative. Now finding out the velocity, x dot is equal to L cos theta theta dot, and y dot is equal to minus L minus sin theta theta dot, so that's equal to L sin theta theta dot. Now we have x dot square plus y dot square, that's equal to L square cos square theta theta dot square plus L square sine square theta theta dot squared. So that gives us L square theta dot square. So the kinetic energy is equal to half m L square theta dot square. Yeah. So now the potential energy V is equal to mg into y, because gravity is in the downward direction. So y is equal to minus L cos theta. So V is equal to, or yeah, mg into minus L cos theta. So that becomes minus mgl cos theta. Now Lagrangian is nothing but t minus v, which gives us half m L square theta dot square plus mgl cos theta. So this is the Lagrangian for the position. This is the fixed point. When the fixed point is considered as the origin, this is what we are going to get as the Lagrangian. Now let us see when this mean position is taken as the origin, what will happen to the x, y and the Lagrangian. Now here the same question of a simple pendulum. We are changing the origin. So simple pendulum, earlier we have used this as the origin, now we are using the mean position as the origin. So here this is 0 0, and this is the point what we want, x comma y. This is as usual L, the length. This is theta. Now you need this as the x, and this is nothing but y. Now the entire length is L. This entire length is L, and we need this particular length as y, and this is x. So x is no doubt x is L sine theta. And what about y? Y is equal to L minus this particular length. And what about this particular length? This is nothing but L cos theta. So y is equal to L minus L cos theta, that is equal to L into 1 minus cos theta. Okay, so x dot is L's cos theta theta dot, and y dot is equal to, L remains as it is, y dot is cos theta, derivative is sine theta, so it's minus plus sine theta theta dot. Right, now x dot square equal to L square cos square theta theta dot squared, and y dot square equal to L square sine square theta theta dot squared. Now kinetic energy equal to half m x dot square plus y dot squared, so that gives you half m. Now x dot square is L square cos square theta theta dot square, and y dot square is L square sine square theta theta dot square, so this becomes L square theta dot squared. Now we need V potential, that is equal to mgy, and here you have from mgy, that's equal to y is L into 1 minus cos theta. So mg L into 1 minus cos theta. Now you can also write down the Lagrangian, which is equal to T minus V half m L square theta dot square minus mgl into 1 minus cos theta. Now this Lagrangian in two different cases, when the origin changes, Lagrangian changes, but Lagrangian equation of motion remains same. Now to understand this Lagrangian equation of motion, let's find out the Lagrangian equation of motion in the two cases. Looking at the two different origin of simple pendulum, we can write the first one from the point of view of the fixed point. We can write the Lagrangian L is equal to half m L square theta dot square plus mgl cos theta. And from the point of view of the mean position, we have the Lagrangian L is equal to half m L square theta dot square minus mgl into 1 minus cos theta. So we have two different values of Lagrangian, but let us look into the equation of motion, Lagrangian equation of motion. In the case of fixed point, dou L d by dt of dou L by dou theta dot minus dou L by dou theta equal to 0. Now d by dt of dou L by dou theta dot, so that's m L square theta dot plus, okay, so that's it, so minus dou L by dou theta. Now dou L by dou theta gives us mgl. Cos theta derivative is minus sin theta. Okay, so this gives us ml square theta double dot plus mgl sin theta. So this is the Lagrangian equation of motion for the fixed point. Looking into the second aspect, or the mean position, equation of motion, d by dt of, and dou L by dou theta remains constant, that is ml square theta dot minus, now we need dou L by dou theta, that's again minus mgl, and with again a minus sign. Cos theta derivative is minus sin theta. Okay, so that gives ml square theta double dot minus minus plus and minus minus plus, so this gives you mgl sin theta. So though the Lagrangians are different, the Lagrangian equation of motion are same. And since Lagrangian equation of motion are same, we say that Lagrangian is invariant. This figure, we have given a string that is attached to two masses, m1 and m2. The string has the length is let us say L, and assuming that this is the origin, we are going to find out the kinetic energy as well as the potential energy of this system. Now if I say this is distance from this point to this point is y, and this length is comparatively negligible, then this distance from this point to this point can be considered as equal to L minus y, because L is the total length of the string, and it is an inextensible string which cannot be extended. So the position of m1, with respect to m1 we have x1 and y1, and the position of m2 is x2 y2. So with respect to m1 we are writing x1, so there is no horizontal motion, that means there is only motion along the y direction, so x1 is 0, and y1 is this one, that's equal to y. Okay, so x1 dot equal to 0, y1 dot equal to y dot. Now looking into the mass m2, we have x2 equal to 0 because there is no horizontal motion, y2 equal to L minus y, x2 dot is 0 and y2 dot equal to minus y dot. Now for m1, the kinetic energy is equal to half m1, so let me write x1 dot square plus y1 dot squared, so that's equal to half m1. x1 dot square is 0, y1 dot square is y dot square. Now for m2, kinetic energy is equal to half m2 x2 dot squared plus y2 dot squared. So here y2 dot square is y dot square, so half m2 y dot square. So the total kinetic energy T is equal to half m1 y dot square plus half m2 y dot squared. So half y dot squared into m1 plus m2. So this is the kinetic energy T. And now looking into the potential energy V1, so it is actually moving downward, so we will write, that means the position is with respect to this position, both y1 and y2 are in the negative direction, so V1 is equal to m1 g y1, V2 equal to m2 g y2. So since here itself we will make a note of that, y1 and y2 L minus y. So this is minus y and this is minus of L minus y. Now this is simply because it's in the negative y direction. So that's equal to m1 g y1. So y1 is minus y and this is equal to m2g into minus L plus y. So that's total potential equal to minus m1g y, then plus m2 g y minus m2 g L. So total Lagrangian L is equal to T minus V. So this gives us half m1 plus m2 into y dot squared minus the V. V is nothing but minus m1 gy plus m2 gy minus m2 gl. So this is the Lagrangian L in the case of this mass and pulley system. Here we have two objects with one with mass m1 and this is m2 corresponding to m1. Let's say this is x1 y1 and here you have x2 y2. Now the best this is attached to a spring of length L, string length L, and probably we will start from this particular point, that is this distance x. So this is our origin, and considering the moment towards this pulley, we will write down the x1 is equal to x and y1 equal to 0 because there is no vertical moment. This is because there is no vertical moment. And now probably x1 dot is equal to x dot and y1 dot equal to 0. This is with respect to mass m1. Similarly, with respect to mass m2, we have x2. So here probably from with respect to mass m2 there is no movement along x direction, so it's 0, and y2 is nothing but the distance it moved. So this particular distance that might have moved, that means whatever distance this displacement it had along x, the same distance will be moved in this direction, that is x, right? Because it is string has a length L which is inextensible. It is rigid string, so it is not extendable. So y2, that means the downward direction would be x. So x2 dot is equal to 0 and y2 dot equal to x dot. Now the kinetic energy is of both kinetic energy, so half m1 x dot squared less half m2 y2 dot square is nothing but x dot square. So kinetic energy equal to half m1 x dot square plus half m2 x dot square. So that is the total kinetic energy. Now considering the potential energy, V is equal to, now the m1, since it doesn't have any displacement along y, it's purely gravity, so there is no potential here. And with respect to m2, there is a displacement that is happening of x, so mgy, and since it is downward, we'll put a minus sign, so it will write it like this, mg minus y, and what is y, and that is y2, and what is y2 equal to x, that's equal to mg x with a minus sign. So this is v. Now Lagrangian is equal to t minus v, which gives us half m1 plus m2 times x dot squared plus mg x. So this is the Lagrangian, and as a practice work, extended work, you can find out equation of motion for this with respect to x. This is a pendulum. This is called double pendulum. And this first one oscillates with theta 1, and the second one oscillates with theta 2, and let the first one have the length L1, this is L2, and here we have mass M1 and mass M2. Now with respect to M1, now what does this double pendulum means? You have a pendulum like this which oscillates in this way, and in the from the center of the second pendulum, the bob, you have another bob which is attached with a string of length L2. Okay. So now this one becomes the x1 and this is y1. Similarly, we have from this point, this is x2, and here we have this distance as y2. Now x1, with respect to m1, we have x1 is equal to this is theta, this is L1, this is L1 sine theta 1, L1 sine theta 1, and y1 is equal to minus L1 because it is in the negative direction. We are assuming that this is the 0 0, this is the origin, and y1 is equal to L1 minus L1 cos theta 1, and m1 and x1 and y1 is done. Now x1 dot is equal to L1 cos theta 1 and cos theta 1 and theta 1 dot, and y1 dot is equal to minus L1 with minus sine theta 1 dot. Now here we have m2 given by m2, that is we need x2 which is equal to we have to include. Now what is the x2? X2 is nothing but x1 plus this x2 with respect to the original point. We have to move, so x2 equal to L1 sine theta 1, that is x1, plus L2 sine theta 2. Similarly, y2 equal to minus L1 cos theta 1 minus L2 cos theta 2, and now we have x2 dot, that's equal to L1 sine theta 1, this is cos theta 1 dot plus L2 sine cos theta 2 dot. Now we have y2 dot equal to minus L1 minus sine theta 1 dot minus L2 minus sine theta 2 dot. So this is x2 dot and y2 dot. Now we need x1 dot square is equal to, so x1 dot square is L1 square cos square theta 1 and theta 1 dot squared. Okay, now y1 dot square equal to L1 square sine square theta 1 dot square. Now x2 dot squared equal to L1 square cos square theta 1 dot squared plus L2 squared cos square theta 2 dot squared. So this is a square plus b square plus 2 times L1 L2 cos theta 1 cos theta 2 theta 1 dot theta 2 dot. Similarly y2 dot squared will be equal to L1 square sine square theta 1 and theta 1 dot squared plus L2 square cos square sine square theta 2 and theta 2 dot squared plus 2 L1 L2 sine theta 1 sine theta 2 theta 1 dot theta 2 dot. So this is x1 dot square, y1 dot square, x2 dot square and y2 dot squared. Considering the mass m1, the kinetic energy of mass m1 is given by, so half m1 x1 dot square plus y1 dot squared, so L1 square theta 1 dot square, so this becomes L1 squared theta 1 dot square. So this is the kinetic energy of mass m1. And considering the mass m2, we have the kinetic energy T2 given by half m2 and x2 dot squared plus y2 dot square, so this becomes L1 square sine square theta plus cos square theta 1 becomes 1 and theta 1 dot square, so that becomes L1 square theta 1 dot squared plus now considering L2 square cos square theta 2 dot square L2 square sine square theta 2 dot square, so it becomes L2 square theta 2 dot squared plus here we have 2 L1 L2 cos theta 1 cos theta 2 theta 1 dot theta 2 dot. Now that becomes 2 L1 L2 cos theta 1 cos theta 1 and cos theta 2 sin theta 1 and sin theta 2. Now that is theta 1 dot theta 2 dot times cos theta 1 cos theta 2 plus sin theta 1 sin theta 2. So cos theta 1 cos theta 2 plus sin theta 1 sin theta 2 is cos of theta 1 minus theta 2, so that's will be equal to half m2 into L1 square theta 1 dot square plus L2 square theta 2 dot squared plus 2 L1 L2 theta 1 dot theta 2 dot. This is cos of theta 1 minus theta 2. So this is the kinetic energy of mass m2 and potential V will be equal to m1 g y1 plus m2 g y2, and that is equal to m1 g y1 is nothing but the first value, that is minus L1 cos theta 1 and that's regarding the first one, plus m2 g, and y2 is minus L1 cos theta 1 minus L2 cos theta 2. So this is the potential energy. So L will be equal to T minus V. This is T is sum of T1 plus T2. So T is equal to T1 plus T2. This is, if you want to consider separately, this is V1, V2. V is equal to V1 plus V2, considering two masses. For practice, here we have a mass m1, which is a block of mass m1 which is moving in x direction. Let us this should be considered as the origin, and in the block m1 there is a pendulum attached, and with respect to this can be theta, and this is length L. Now the question is to find the Lagrangian of the system. Here we have a pendulum with a spring attached. So this length is together L, and this particular length which extends and contracts is R. So R is a variable here, which means L plus R is going to be a variable, with R being the variable term. So this is theta, and let this be the L plus R cos theta, L plus R cos theta, and here we have L plus R sin theta. Now x, that is this distance, is L plus R sin theta, and y is equal to L plus R cos theta, and assuming that this is the origin, the y is having a minus sign. Now x dot is L plus R sin theta, differentiation is cos theta, and theta dot plus R dot sin theta. So this becomes x dot. Y dot is equal to L plus R, the minus sign, cos theta, differentiation is minus sin theta, theta dot plus minus of L plus R, minus of R dot cos theta. So that's equal to L plus R, minus get cancelled. So L plus R times sin theta, theta dot minus R dot cos theta. So now we have this x dot and y dot. So x dot square plus y dot squared is equal to L plus R whole square cos square theta theta dot square plus R dot square sin square theta plus 2 times L plus R cos theta and sin theta from here and R dot theta dot. Again, with respect to y dot, so adding y dot square here, so plus y is L plus R whole square, L plus R whole square sin square theta theta dot squared plus R dot square cos square theta. So this is plus and this is a minus b, so that means minus 2 times L plus R sin theta cos theta sin theta cos theta R dot theta dot R dot theta dot. Now in this, the last term from here and here gets cancelled, so this becomes L plus R, so this becomes L plus R whole square theta dot squared plus R dot square plus R dot square. Now if you want to get the kinetic energy T, we have to multiply this with half m, which is mass of the ball, and potential V is equal to mg into y, and y is minus L plus R cos theta, so that's equal to mg into minus L plus R cos theta. So that's about the V, so which means Lagrangian L is equal to half m L plus R whole square theta dot square plus R dot square plus mg into L plus R cos theta. So this is the Lagrangian, which is T minus B. Okay, for the spring pendulum.